Hello everyone. Hello everyone, welcome to my presentation. Today I will present a topic variational analysis for CNC milling process. This presentation have four parts. Part 1 is introduction, part 2 is methodology, part 3 is result, and the last one, part 1, the last part is conclusion. So we begin with introduction. Accuracy of machining process strongly depends on the ability in driving the machine tooltip along the nominal cutting path defined by the machine control system. In CNC machine, the nominal position of the tooltip derived from the preparatory function writing in the ISO 6983 part program and interpreted by the control unit, which drives the machine actuators and measure their position. The calibration process could be faster and machine process could be more accurate if the contribution to the position errors of the tooltips are minimized according to an innovative design process where the different error sources are simulated and evaluated. In order to forecast the past structure of the produced machine, the modern computer-aided engineer tools allow for analyzing and simulating the behavior of the complex system. At the CNC machine CAE analysis can be used to evaluate the position errors of the tooltip, taking into account a defined set of error sources, geometrical defects, kinematics, behavior, thermal deformation, static and dynamic loads. In this paper, different CAE tools provide solutions to forecast the position errors of the tooltip in a specific CNC machine when considering a set of error sources that affect the geometry of the machine and the position of its tooltip. Broadly, machining errors depend on two major error sources: motion errors and the motion error of the machine tool system, and errors due to the machining process. Major causes of errors in the machine tool system include imperfection and misalignment of guideway of sliding stage. The assembly errors of the alignment of each axis, the non-parallelism of guideway, and profile errors of guideways affect the accuracy of three-axis machine tool. Errors due to the machining process have direct effect on the geometric accuracy of the machine surface. They include mainly cutting force variation, which cause tool deflection, and thermal effects, which deform the tool. All the sources of errors are addressed in the scientific literature. A great number of researches related to the tool error in cutting process have done. Variation simulation analysis (VSA) kinematics model and FEM analysis could be significantly merged to create a model that figure out the possible position errors of the tooltip in working volume, determining the variation of the relative positioning of parts with tolerances in an assembly is a key problem in assembly planning and mechanism design. Tolerance analysis is a critical step to design and build a robust here problems may present during the assembly process if the tolerance study on a subcomponent was not carried out or was ineffectual. Many well-known approaches exist in the literature to the tolerance analysis: the direct linearization method, affine matrix algebra, and root-sum squares errors analysis to the vector loop space model to estimate tolerance stack-up assemblies. The proportion assembly clearance volume methods create 3D dimension change by using small displacement torso concept. However, the methods are not easy to apply, especially for complex assembly, so the aid of computer is called for. Today, computer aided tolerance software is readily available. The recent work considers a CNC milling machine in order to study the influence of the tolerance assigned to the assembly component in different positions of the assist. We move to the second part, a methodology. We have 5 methodology: is product and manufacturing information, geometric dimension and tolerances, kinematic analysis, thermal analysis, and finite element analysis. The first methodology is BMI. BMI dimension and tolerances, 3D and annotation, surface finishing and material specification. BMI not only reduce the need to generate 2D drawing, it also enables downstream application to directly access this information for automating tasks such as CNC programming, tolerance stack-up analysis, and CMM analysis. Through the use of 3D documentation methods, the time and cost of documenting a part can be reduced by 50% and make easily involvement of manufacturing easier with state-of-the-art online 3D collaboration and visualization tools. We move to the next methodology, is geometric dimensioning and tolerancing, GD&T. According to the BMI approach, a complete set of dimensional and geometrical tolerances describes the errors admissible on the component of the CNC machine. The simplified model is illustrated in Figure 3. It allows a faster analysis of error contributor, and in Figure 4 we just illustrated the tolerances applied to the base of the CNC machine. Table 1 illustrated a list of assigned tolerance for the simplified model, but the real manufacturing data are rarely shared with research organisms, so we extrapolated the tolerance value from the general tolerances describable in the standard ISO 2768. We move to the next methodology. A kinematic analysis. At the end of the simulation, we have a result that is the merging of GD&T and kinematic analysis for the CNC machine. The motion of sliding stage along the guideways modify the interaction of geometrical defects applied to the CAD model of CNC machine component. A reliable analysis of tooltip displacement should take into account the different positions of the sliding stage. We apply discretization of the working volume by consider 27 points located on the 3 different surfaces along head transfer axis. Each surface contains 9 points, so the total number is 27. In Figure 5, they illustrated the discrete working volume and relationship with the whole machine. In a kinematic chain create link from the tooltip attached to the machine head to the manufacturer and part lying on the machine table. In Figure 6 illustrated 3 different configuration of 27 ones has been provided. For the for methodology is thermal analysis. Continuous uses of machine tools cause head generation at the moving element and head cause expansion of the various structure element of the machine tool. Some of the possible head sources are boring, girl and hydraulic oil, dry and clutches, pump and motors, guideways, cutting action and swap, and external head sources. The final methodology is finite element analysis. The present study developed a finite element model along with an and milling machine structure model to analyze the tooltip error in the milling process of workpiece. In Figure 3, we introduce the preliminary model for FEM analysis in order to see the effect of the stated loads on the tooltip position. We create the assembly of FEM in order to have whole part in their position respect to the other one. Figure 7 illustrated the detail of FEM model developed for finite element analysis. And we move to part 3 is result. The tooltip due to geometrical deformation and defects is obtained bin of VSA tool. It is shown in the figure A. The model critical situation is in the Z direction where half the load SCBK is illustrated in table 2. In figure 9, the final position errors in the CNC machine configuration. As a result, we could figure out the behavior of tooltip due to the geometrical defects illustrated in Fig 10, and Fig 11 illustrated the effects of stated loads on the head and the table of the CNC machine. And the last one is conclusion. We have model improvement and software improvement. In model improvement, we should improve the integration of the result of different analysis. Such integration is operating on CD&T kinematic analysis, but it should be improved in order to integrate FEA results. And software improvement, we have 3 methods. Improve the PMI method, link the GT file with the process document, and improve the kinematic assembly operation of the team center visualization. So this is all about my presentation. Sincerely thank you for your listening.